Okay, this is the Unit 3 statistics notes. This is going to be Unit 3-1. So I've given you the first page just so that you'll be able to separate your notes. 3-1 is talking about probability experiments. The probability experiment is an action or a trial through which specific results are obtained through simulations. So we've talked about the different ways that you can have a do statistics, get data. The fourth version was called a simulation, and that is what we're talking about when you're doing probability. So the probability experiment consists of tossing a turn, then rolling a six-sided dice. So the first action was tossing the coin. The second action is rolling the dice. And we're going to determine the number of outcomes and identify the sample space. A sample space is all of the different ways that the first action and the second action can be combined, the results of it. So we can use a tree diagram, and in that we will pick the coin first. You can get a heads or you can get a tails. Then we would roll the dice. Well, when you roll the dice, you can get a 1, 2, 3, 4, 5, or 6. And that happens whether you have a heads or a tails, so it would be the same options for both choices. And then we see the combinations. So H1, a heads first on the coin, and then getting a 1 on the die. So that would be the first choice. Heads 2, heads 3, heads 4, heads 5, heads 6. That would be the possible choices of a heads on the coin and rolling the dice, the different choices on the dice. And we do the same thing with tails. Tails 1, 2, 3, 4, 5, 6. So there are 12 possible outcomes. So the sample space, the N, is 12. So this is talking about the N. Okay. Now, a simple event is an event that only has one single outcome. So an example would be getting a 1 when rolling the one die. So as long as all you're looking for is a 1, there's only one way of getting that on a single dice. The star on the Texas flag, there's only one star on the Lone Star flag. That's why it's called the Lone Star flag. A non-example would be picking white cloth on the Texas flag. So if you look at the Texas flag, there is actually 2 different places on the flag that is white. The star is white and one of the stripes is white. So that is a non-example because there are 2 outcomes possible. Okay, so you're going to look at these 3 examples and we're going to kind of work these out together. The first one is you are given a bag of 12 marbles. 3 are blue, 2 are red, and 7 are green. And event A is getting a red or a blue. So just from the fact that you have 2 possible choices as being okay, as good, means that you are not doing a simple event, because there are 3 blue in there and 2 red, and you have 2 potential choices. So this would be a no because of 2 choices, red or blue. So that is not a simple event. You ask a student's height measurement at his or her last visit of doctor. Event A is determining if the student's height was 60 inches. So you will only get one response on their last visit. So that is because there's only one, it's a yes or no. Well, this would be a yes because their height will have one number. You are given a basket that includes one of each of the letters of the alphabet. The event is selecting a vowel. So this one's a no, simply because how many vowels are there? Well, there's A, E, I, O, and U. So this one was a yes. The second one was a yes because there's only one number that they would provide for their height. The others had more than one choice that could have been an acceptable choice. Okay, a fundamental counting principle is a way to count up the number of choices when you have different items being chosen from. So like shirts, pants, socks, shoes. those are all different types of clothing, and we can combine them in different ways. So if an event has m ways, m number of ways, and the second event has n number of ways, the number of ways those two events can occur together in sequence is m times n. So basically, if you had 4 manufacturers, 2 car sizes, and 3 colors, then you would have m times n times o, or 4 times 2 times 3, 24 different ways. Now, we could write out a tree diagram like the first example and get that same 24. This is just a faster way of doing it. Fundamental counting principle. So let's do another example. The access code of your home security consists of 3 digits. Each digit has the numbers between 0 and 9. So there's actually 10 digits. So counting 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. How many different combinations? Well, each dial is separate. So those are separate dials being used. And that therefore you have 10 choices on the first one, you have 10 choices on the second one, and 10 choices on the third one, and they don't affect each other. And that gives you a total of 1,000 different combinations. So I'm going to let you do the second one. Use the same idea. Again, codes are possible if the digit can be used only once and not repeated, changes how many choices. So on the first choice, we get 10 choices, but the second time, if 1 is used here, 1 can't be used here. If one is used here, 2 is used here, then 1 and 2 cannot be used here. So that's going to change your numbers on this one. Okay, traditional classical probability is a traditional probability, the kind that we thought of when we were in elementary school. When you flip a coin, they ask you what's the probability of getting heads. That's called classical, theoretical, or traditional. It means the same thing. That is where every sample and every element in the sample is equally likely to occur. You're like 50% chance of getting head, 50% chance of getting tails. Empirical probability involves experiment. You physically have to flip the coin and you record your responses each time. What you'll find is classical and empirical don't necessarily match. You would expect, because the theoretical says that you have a 50% chance of getting heads, you would expect the coin to flip on heads, the next time on tails, the next time on heads, etc. That doesn't happen. And then subjective probability is a result from intuition, educated guesses, and estimates. The things like I believe. I believe based on experience that 70% of the students will pass a specific class. That's based on past experience. But it is a belief. It is not based on experiment or on a theory. It is based on past educated guesses and estimates. Subjective probability is probably the most difficult to understand because it is a guess. Okay, classical probability, which is again theoretical, is found by the number of outcomes in the event divided by the number of outcomes in the sample space. So the things that match what you're looking for over how many possible ways that you could have gotten a response at all. So event A is rolling a 6-sided dice and getting a 3. Well, on a 6-sided dice, there's only one 3. So there's only one chance out of that 6 sides to get a 3. So that's your probability of the event. And then 6 is the number of different sides that you could have chosen from. So there are 6 sides, therefore 6. So our probability of a 3, this is how we read it, probability of 3 is equal to 1 divided by 6, or 0.167. Okay, so let's do some examples, finding the probability of a deck of cards. A couple things to note, because I found this out. A lot of kids don't know there are 52 cards in a deck. There are 13 that are diamonds, 13 that are hearts, 13 that are clovers, and 13 that are spades. And I don't remember how to draw a spade. Spade. Oh, that's a diamond. Let's just write spade because I can't remember how to draw it. Okay, so you select a card from the standard deck, the probability of getting a Queen of Hearts. Well, in each one of these sets, there's one of every card type. So there's only one Queen that is a heart out of the entire 52 decks, 52 cards in a deck. So your probability of a Queen of Hearts is 1 out of 52 because there are 52 cards to choose from and only one of them matches that specific explanation. You select a card and find the probability of getting a diamond. Well, there are 13 diamonds in the 52 card deck, so the probability of getting a diamond is 13 out of 52. So now that you've seen a couple of examples, what's the probability of getting a diamond or a club? So remember, or means you could choose either one and that would be fine. So that means you have to combine the number of each of those types to get your top number, okay? But you're still pulling from the same size deck. Okay, so if you got 26 out of 52, or 1/2, you would have had the right probability. Okay, and this, by the way, is 1/4. Okay, so a probability for experimental probability involves the frequency of the event divided by the total frequency. So here's where we have taken a survey and they asked 1,904 people, that's our N, whether they would be voting Republican, Democrat, or Independent, or didn't know. Okay, kind of appropriate for our current world. And we want to know what's the probability the next person surveyed is going to be a Democrat. Okay, so based on past experience, we can make a prediction for future experience. This is our prediction. This is our past actual numbers. So we find out how many are Democrat, because that's what we were looking for, out of how many total people were in the past surveyed, 1,904. So 852 divided by 1904 says that there's 45%, basically 45% of responders are Democrats. So there's a 45% chance that the next person they call will be a Democrat. Okay? Okay, so a toy manufacturer determines that in 1,342 balls, 5 will be deflated. So the event that they find a deflated ball would be 5 from past experience out of 1,342. So they have less than a 1% chance, a 0.004 chance of having a deflated ball coming through. That's how warranties are figured out. So we have an example of a ice cream company, and they are testing new flavors. And the tester will prefer the Banana Blast. So we take Banana Blast out of the total number of people that they did in the past already. And 51%, 52% will want Banana Blast. So what these are examples are real world situations. A company trying to decide what percentage of basketballs should we expect to have to worry about for our warranties, and what new flavor should become the new flavor that we put out in our ice cream shop. You would not want to put the thing out that the least percentage of people liked. Okay, so law of large numbers, it involves this. So an experiment is repeated over and over again, and the empirical probability of the event finally approaches theoretical. As you do more experiments, your results will get closer to the theoretical expectation. So give an example of a large number. How do you find it? Well, these probabilities results from intuition for subjective probability. How do you find it? They come from intuition, guesses, and estimates. So what you're going to do is you would look at past experience and then make a future explanation or future guess. That does not mean that it's going to be accurate. So based on past experience, if you roll a dice so many times, you might see 5 come up. Or if you look at the lottery, you might see a certain numbers repeated more often than others. So based on that, you would guess that those would be the next group of numbers to win. Doesn't mean that that's going to happen. Okay, so here's 3 examples, types of probability. The probability that the next person to purchase Jimmy Joe's barbecue boom sauce is older than 40 years old, it's 0.23. That is based on experience, and it is based on the past records. So that would be a empirical because it's based on experience, not a guess. The probability of choosing the letter D from a jar containing the letters is 1 out of 26. That is classical because we know there's 26 letters in the alphabet and we know there's only one D, so there's only one way that you're going to get, and that's a classical. Probability that there will be a major tsunami event in Hawaii in the next 50 years is 0.09. Now, that could be empirical or subjective. Most likely, it is empirical based on past experience. If they said that the probability that there would be a tsunami this year, then that would probably be subjective because you're making a guess and it's not really based on past years' experience. It all depends on where the data is coming from. Okay, range of probability rules. Probability of an event is between 0 and 1. It can be 0, it can be 1, which would be 100%, but it can't be bigger than 1. If you ever get a number bigger than 1, you are doing it wrong. If the probability of a certain event is 1, then the event is certain. If the probability is 0, it is impossible. And if the probability of the event is 0.5, it has an even chance of occurring. So 50-50%. Probability of a complement of an event. So sometimes we have a lot of other choices and we want to know the probability that this is not going to happen. Okay. So if we know the probability of something happening, ages 25 to 34 happens, and that's this probability, then we can take it away from 1, because remember, they always add up to 1, and we will find the probability of all the rest of them happening. So the probability of not being 25 to 34 would be 634 out of 1,000. If we added up all of the checked pieces, they should add up to 634, and the entire column added up to 1,000. So we could have done this either way. This is just a shortcut. It makes it lots faster. Okay, that is the end of 3-1.